Hello and welcome to this webinar. I will be your host today. I'm Lutz Stratmann from PalmSens. I'm an electrochemist. With me is my colleague Adi van den Berg, who is my technical support and your voice in the chat. Again, as a reminder, if you want to interact with us, use the chat function at the bottom of Zoom. Adi will read all the time the chat and then convey messages to us and ask us questions. So who is us? Well, we have a star guest today. We have Kordel France here, who is working for Toyota at the moment as a principal AI engineer and a technical lead for robotics. He has an education with a master's degree on reinforced learning and swarm intelligence from Johns Hopkins University, then started to work at the University of Texas in Dallas. And now he's doing his PhD under the supervision of Dr. Oviedo Deshko, also in Texas, and about on adaptive learning in machine olfaction for robotics. Because all this is not keeping him completely occupied, he has worked on an app called Sentience, where he wants to enable everybody to use olfactory sensors in real time for robotics in an easy way. So for this, he has used, by the way, a lot of our OEM products, like our EmStat Pico was used because it's very small and easy to integrate into robotics. But if you're looking more for batch solutions, you can work with our EmStat 4T, where you have a handheld solution. Okay. Also, after the webinar, if you visit Kordel's website, you can find a lot of podcasts because he has done AI programming for a long time. He did AI before it was cool. And with these words, I would like to give the floor to Kordel.
Thanks, Lutz. Thanks, Artie. All right, good morning, good afternoon, everyone. I'd like to talk to you today about how we can enable olfaction for robotics through electrochemistry. So I started getting involved into olfaction or the machine sense of smell by looking at breath. And I will go into that in a moment. But when I started working in the field of olfaction, I noticed there were a few reasons on why it's not a prominent modality in AI and robotics. If we look at computer vision and we look at some of these other modalities, we see a lot of research, but the sense of smell is not as highly regarded or as highly researched artificially for robotics. And so I set out trying to understand three problems that, I kind of deduced three major problems to why this was. There's a lack of robust olfactory sensors for robotics, a lack of tools available for AI researchers and roboticists to look at olfactory sensors, and there's no data standard for the sense of smell. We have JPEGs and PNGs for images, .vec files, .wav files for audios, but we don't have a standardized format for the sense of smell. So I spent a lot of the last few years trying to contribute to these three major goals. Again, if we look at the other aspects of all the human senses, we see that olfaction in a research and capital perspective is significantly underallocated in proportion to its counterparts. So I mentioned that we started looking at breath. The goal that we were trying to accomplish with our initial intent was to understand if we could assess different medical conditions in the body by analyzing the chemicals in your breath. So basically, you breathe into a breathalyzer. Apologies. You breathe into a breathalyzer, you trap the air, you analyze it, and try to deduce and segregate different chemicals that might indicate various statuses of things going on in your body. And while this is, we learned a lot doing this, it is a little bit simpler, I'd argue, because you're kind of trapping the air and you're just looking at it in a static sense. You trap it in a chamber and you start analyzing it. And this can take several seconds. If anyone has worked in electrochemistry or chemical sensors, we all know that they usually take several seconds, if not minutes, or in the case of a GCMS, maybe hours to assess an air sample. And if we look in the robotics perspective, that's not really feasible because all the other sensors in robotics and AI are they're very short. You have cameras that can look at several frames per second. We have audio that can look at several samples per second. Chemical sensors don't have that analog. And so one of my main goals was trying to take what I learned from breath and make the measurement sequence shorter. So if we look at amperometry, where we're looking at very long sequences in the past, and I tried to understand if we could infer the reduction potential by and make the sequence shorter. So there are a couple papers out there on that, and I took inspiration from what was done in previous sensor types like metal oxide sensors. And this effectively compress the frame rate into something that was a little more tractable, something not quite on the frame rate of like cameras, where you get hundreds of frames per second, but better than 30 seconds, 60 seconds, et cetera, that we might otherwise see for various electrochemical techniques. So I took the learnings here and I applied it to robotic navigation by scent. I'm really, really interested in solving this because we see that it's very effective by several organisms throughout the world, but it's not really solved in an artificial sense. So I took some electrochemical sensors, attached them to a drone, and I'll actually show you really quick. I like to show hardware so people know that things are real. Attached it to a drone, and then basically told it to go find the source of a chemical. And so we have electrochemical sensors on the antenna here, and then a processing unit, or olfactory processing unit on the bottom that enables this drone to navigate by scent. And analogously, you can do that for any robotic sensing platform, not just a flying drone. Perfect. So this allowed us to basically say things like, go find the source of compound X, or tell me from where this chemical is coming from. If we look at like ChatGPT, that has the ability to interpret images, generate images, interpret audio, generate audio, and understand natural language, it doesn't have the ability to measure the chemical world because it doesn't have olfaction sensors, and the training data is not substantial for chemical or an olfaction itself. So if we can give these types of capabilities to something like ChatGPT, we can allow it to understand the chemical world around it, to say, from where is the source of ethanol coming in this image? If you do this in ChatGPT right now, it's not super great at it, but I'm hoping to change that. So with this work, I felt like I contributed at least to the first major problem that I saw. And then I wanted to move on to tackle the next problem, which is the lack of olfaction tools available for AI and roboticists throughout the community. So a lot of the tools that existed were basically, they're usable in the lab, but if you want to do real world data collection for training world models or simulations in robotics, the tools weren't there exactly in order to that roboticists and AI researchers were used to. And so I set out trying to build a tool called Sentience that allowed real-time interface with different chemical processors. And I built my own the same processor that I used on the drone. I interfaced with the app so that you can get real-time data. And then I also open it up to other third-party vendors like PalmSens that allow you to, for example, communicate with the Pico dev boards or other PalmSens hardware. So it was originally just a tool I built for myself to communicate with the sensors that I was putting on these robotic platforms. But after speaking with others in the community, they requested that I let them use it. And so I pushed it out, made it publicly accessible so that everyone else in the community could benefit from it. So this acts as like an olfactory interface that one can use to interface with or to communicate with different chemical sensors, get real-time data, export that data, export an analysis, if you will, so that you can do post-processing of it and other things. On that app, there's an olfaction-vision-language-model. So if we have language models, we have vision language models. Intuitively, it makes sense to extrapolate to an olfaction-vision-language model. So I worked to train that model and build something that could easily understand all these modalities together and contextualize them into something that could be a little more intelligible about the chemical world around us. This runs fully at the edge, and to my knowledge, it is the first actual introduction of olfaction vision language models to AI. So with this in mind, I felt like I contributed somewhat to the second problem that I saw, And I wanted to finally address the third problem that I identified a few years ago, which is there being no data standard for the sense of smell. And part of this reason is because there's not a lot of large data sets, or there's disparate data sets available to the world for olfaction. Because we have different sensing types, we have electrochemical sensors, metal oxide sensors, optical sensors, acoustic sensors, that creates different data types, which creates different data sets. And so to detect chemicals, some of the arguments I've gotten from the AI community is we don't know which one to use, which one's ground truth. And the answer is, well, all of them are true. We just need to harmonize them a bit better. So I built another tool called Sigma that allowed me to multiplex all of these modalities together and get time sequence data for electrochemical or electrochemistry, audio, vision, inertia or inertial data, and language all together into a single application, so that I had all these modalities to inform how chemicals are changing in the world around us. So if I want to understand how to do scent-based navigation better, it is not only prudent to acquire chemical data, but visual data and inertial data to understand how the robot moves throughout the world and how it's associating chemicals or molecules with visual objects around it. So again, this is a tool I built for myself, and just to make progress in acquiring data, but it came at a request of others to open source and make it accessible to them. And so I actually just open sourced this on Monday to allow others to use the device and the app as well. This device that you see on the screen leverages a PalmSens hardware to do some of the processing inside, and it also interfaces with several other olfaction sensors besides electrochemistry as well, to get a comprehensive view of the chemical world around us. I built the device to be able to adapt to different connectors so that we can put different sensors on it. Maybe we want to run 3 or 4 electrochemical sensors at once, or we want to run just 1 or 2. This allows us to easily swap those out. And then the app that works with it gives you real-time data similar to the Sentience app I just showed, but this is a bit different because it's running fully at the edge and acquiring data. Whereas this is meant as a mass data collector, versus the other app is meant more of an olfactory interface for analysis instead of acquiring data. So I've made this available to the community, and I hope that we can get more people involved with olfaction within AI and robotics to try to move the sense of smell in proportion to the other modalities that AI and robotics are training on today, to give a more comprehensive view of intelligence. And in doing that, electrochemistry is a significant contributor to being able to achieve olfaction because of the science. So with that in mind, I feel like this last effort that I've made maybe contributes to that third point, that third delinquency I saw. There's still a lot of work to do, and I don't feel like we're even close to being done to materializing the sense of smell from machines. But if these tools can help bring more access to the community for the sense of smell for robotics, then I hope we're all the better for it. With that in mind, I'll open it up to questions and turn it back over to Lutz and Artie, and anything that you might want to zoom in on. Thank you.
Thank you, Kordel, for the presentation. I already see that there are some messages. And yeah, Artie, do we already have questions?
Yes, we do actually. We have already 2 questions. I'll start with the first questions. And this is for you, of course, Kordel. So then, regarding the drone that you showed in the beginning, is this the navigation of the drone? Is it specific or is it specifically applied to a closed space or an open space?
So it's meant for both. The open space is much harder because you have to infer different wind models and wind dynamics. If you're in a closed space, you have HVAC systems which you can turn on or off. And while those things make things complex, I found they're a little more predictable than the wind outside. So it is. I'm still working. My work focused on trying to solve indoor navigation first, and then trying to extrapolate that to outdoor navigation. And the principles translate well, but it is much harder to do outdoor navigation than indoor navigation from what I've seen.
There, like a follow-up question, maybe. how do you do that with the navigation and the moving of smell? I mean, let's say there is a heater, it will create convection, and so the chemicals are spreading differently in the room. Is that also like an AI model that then follows typical movements of convection indoors or outdoors? Or is that like, do you apply multiple sensors and measure the differences to find the orientation? How does that work?
So I apply multiple sensors and try to take the difference between them or take temporal difference in readings. But the best way to do it is the method you suggest personally, where is if we can understand how chemicals and molecules evolve with the world as it's being as the robots interacting with it, that's the best way to go. And that's actually different than some of the other modalities that AI is training on. So if I'm doing image recognition, the image is kind of static and it might not change, but the chemical you might be tracking with the robot, it might change over time based on chemical reactions and oxidation of just different molecules around in the air. And so it's important to understand how your target compound changes throughout time and throughout the world, which is actually difficult. Like that's actually pretty computationally complex to have a generalized solution, especially that runs very fast to a degree that robots can make sense of it several times per second. So that's a very high computational way, but that's the right way to do it. So if we can have more focused efforts on the community on how to compress that into a smaller edge-like model, then it'll be much faster, and that's the most efficient way to do it. But if you have a very specific compound you're looking at, you might be, and you know it's not going to react within a finite amount of time, you might be able to get away without that chemical model, that chemical prediction model. But either way, it's extremely valuable and needed.
All right, great. Thank you, Korderl. And this is a message for everyone, actually. So there are already quite a few questions in the Q&A here. You can upvote them if you like. So if you typically like a question a lot, you can upvote them, and then we answer them first. But let's go now to another question, also regarding the drones, Korderl. So this stirs something up. The question is like, does the operation of the drone itself, because of course you have these rotors, do they also interfere with the recognition of the airflow, let's say, past the sensors or not?
Yes, it definitely does. That was one of the most difficult problems to solve because you have to adjust, you have to understand, like there's actually a lot of computational fluid dynamics that could be helpful here. And if you look at some of the other research that has been done to understand how the rotor wash from a quadcopter or even like how a robot, just like a humanoid robot, and the airflow around that, it changes as the robot moves throughout the world, they can get pretty complex. But what we found is that there's a distance you have to be above the ground because the rotors will push down the air and they can kind of help you by pulling in air towards you, but they also can push air away and distort the signal. So if you think of like how a moth has antennae that stick out, it's away from the beating of its wings. And I think that's like a natural indication that, okay, we'll put the antenna away from the rotors. And so we stuck the antenna way out, if you can see on the screen here. We've stuck the antenna way out past the rotors to try to escape the noise that they can cause. But it's not a perfect solution. And if you have a really big drone, it's going to create a lot of turbulence, and then you might have diminishing effects. So there's a sweet spot on how high, how large you can go, and how much payload you can have on the drone. But yes, it definitely does interfere, and it must be modeled for.
Very clear, Korderl. And another question from Eric Young, actually, and he wants to know. Well, he mentions like that there are examples in nature like the night moth, and they can measure extremely low concentrations. And yeah, how accurate can your current your solution with the PalmSens module? How accurate can that measure?
So my solution is not as accurate as a night moth or a dog or something like like a petrel, like some of these birds that navigate by scent. And that's not a fault of the PalmSens module. That's just the current state of where I am with things. If you look at like a part per trillion or a part per quadrillion accuracy, very difficult to get with navigation by scent right now, at least in my work, because like moths and dogs can track a scent for kilometers. And they only need a few particles in order to track that scent. And they have these very interesting surging and casting techniques in order to acquire that scent trail. And sometimes you can go several time steps without a chemical measurement. So you're actually like measuring blanks. And that part's actually difficult to understand. Well, should I keep going in my original direction, or should I change directions, go somewhere else because the chemical plume has changed in a different direction? That's actually a pretty difficult thing to solve, and that's what I'm working on right now, is trying to understand, like, how do we do several kilometers worth of scent tracking? We know it can be done because it's been done in nature. My work's focused only on meters worth so far.
Right, thank you.
But how about quantification? Like, which concentrations are we talking about?
I'm working in the parts per million and parts per billion concentrations right now, but uh, I know that dogs can sense in the part per trillion, and there are a couple research papers that suggest certain hounds can look at part per quadrillion. I'm not a neuroscientist, so I can't quantify whether or not that's true. But if that's the case, we have a long way to go to catch up with nature.
That sounds good. A question from Tony Cass, and he has a question about specificity. So yeah, in nature, he mentioned that the receptors are often non-specific, or there is cross-reactivity. How many receptors do you think will be necessary for machine olfaction?
That's a good question. It seems likely that we'll need at least hundreds of receptors to be any sort of to meaningfully generalize in any way. Like I showed the drone and the device here that just has a few receptors that's trying to get information about the world. But we have most beings have hundreds of receptors, if not thousands, of different coded olfactory receptors, and that most of them, from my analysis, it seems like they behave kind of like piano keys, where you don't hundreds of receptors doesn't mean you can only detect 100 compounds, because you have the combinatorial permutations of all of those that are like piano keys that can give you thousands or tens of thousands of different chemicals that you can understand, different aromas. And so, if we can find a way to put thousands of receptors and multiplex them in a way that's fast, that seems like it'd be the most efficient that's the most efficient way to go about this. And we see some research on this already, but it's not compressible to a point that, from what I've seen, we can put on a mobile robot. So there's a continuum where it's like we have lots of sensors that can run in a slow amount of time, or we have a few sensors that can run very fast and that can fit on a robot. Hopefully we can get this latter part of the continuum up towards the former part, so that we can get extremely specific sensing that runs in several times per second.
Thank you, Kordel. Another question, an anonymous one. From your experience, how does the electrochemical sensing compare to metal oxide sensors in terms of drift, selectivity, and robustness for mobile robotics?
So the metal oxide sensors that I work with all different types of sensors, because I think it's important for me to understand the pros and cons of each and the limits of where we can go. So what I've used so far is I use basically metal oxide sensors to get a general sense of the chemical presence around me, and then I use electrochemical sensors to hone in on one specific chemical that I'm trying to track. So electrochemistry will allow me to get a little more specific. But metal oxide allows me to look at kind of an umbrella. And metal oxide sensors are pretty fast, especially with some of the work that's been done by Dr. Dendler from ETH Zurich to speed them up and make them, sample several hundred times per second even. But the drift is definitely something that must be accounted for because of the heating element for a lot of these sensors. And with the electrochemical sensors, I work with ionic liquids, and those get saturated over time. So you have to reset them by doing something like joule heating, or you've got to replace the sensor or replace the RTIL, all of which contribute to drift. So a lot of like the software I built is just trying to understand, is the sensor drifting? Like, is the sensor I'm receiving actually true signal, or does this incorporate some drift over time? And how do we take out that temporal misalignment? So to answer your question, the drift is a significant impact, and I haven't found like a generalized solution that allows me to characterize drift across all chemical sensors, they all or metal oxide and electrochemical sensors, they seem to need to take their own different drift characterization profiles to some degree. That takes time to learn and train, especially for each different sensor type and chemical electrochemical type.
All right, then a question about the sensors that you're using and for specific applications. How did you obtain these sensors? How did you get them? Did you buy them from somewhere else, or did you make them yourself in-house? Could you explain a bit more about that?
Yeah, the sensors that the electrochemical sensors I'm using, I buy off the shelf because if I use a standard sensor, or if I build my own sensor and then I don't publish that to the rest of the community, they can't replicate the results, right? So all the sensors I buy are typically they're just through various vendors. I buy a lot of electrochemical sensors through PalmSens. I put a lot of custom software on there, but the hardware itself, I've intentionally tried to standardize or maintain a standard of buying from what's available to see how far I can take those so that my results are reproducible by everyone else.
All right, but you didn't functionalize the sensors yourself, or did you do that yourself as well? Like,
functionalize.
Did you so the sensor that you use? So you bought them from a third party, and did you then make them react to a certain molecule or a certain biomarker yourself?
Yes.
Oh yeah, okay.
Yes, we coat them with like ionic liquids to get them to react to specific biomarkers. So the hardware itself is purchased from third parties that anyone can get, and then we put specific ionic liquids, also third party, and tune the tune the parameters for various electrochemical techniques to understand or to track a specific compound.
Great, thank you. Are there similar approaches based on the sparse data known from the visual sensors also applicable to olfactory that you know of?
Yes, I think so. Not I think so. I know so. There's a lot of good work on sparse data in vision and audio that can be extrapolated to olfaction, and some of it would be. It seems pretty intuitive. I have some of them I've tried and they work well, but it would be worth trying to get other people from the AI and robotics community to bring some of that work that's been done in sparse coding for olfaction. I mean, literally, just if we look at some of these papers and we can just translate it to chemical sensing, that could have significant results. So I don't think it might not take any new techniques, or it might, I don't know, but it's a good start to just look at what's been done in computer vision and audio and try to translate that into olfaction.
Right, and now a forensic question, Kordel. Have you considered applications like gunshot residue testing for forensic analysis?
Yes, so we tried to look at proxy chemicals for that's not necessarily for gunshot testing specifically, but could be used like sulfur dioxide or some other chemicals that are components of gunshots or other types of substances. And I mean, the thing that's difficult about that is again understanding like if you look at gunshot residue, how long has it been there? Because it might look differently if it's been there for 10 minutes or if it's been there for 10 days. And so, like, what concentration are we looking at? And is that due to the fact that there's been a lot of off-gassing going on, or are we very close to the source? So those types of questions on gunshot residue I think, are still, at least from my experience, are not quite well answered yet. But the principles could translate from everything I've done to such applications.
Exactly, right.
There are also like a small follow-up question, maybe. How do you have examples of the olfactory sensors that you have successfully used in robotics? Like, so which compounds have you been able to detect?
Oh, a lot of what I've focused on is ethanol and toluene and nitric oxide. So a lot of nitric oxide for medical applications, and toluene, ethanol, acetone, benzenes, and some other aromatic compounds. Those are what we've had success in testing. And ethanol is a good chemical, because a good compound to use for robotics, because a lot of the other work in olfaction and robotics uses ethanol as like the baseline proxy. So you can kind of build off of results and eliminate your compound as a variable if you use ethanol, because it's kind of I won't say normalized, but there's a lot of previous work in it that makes it a little bit more understood. So I try to use that as like the springboard for everything else. It's like, if we get to work with ethanol, can we extrapolate results to other chemicals like toluene, sulfur dioxide, nitrogen dioxide, etc.
All right. And the next question, Lutz, is actually for you. It's about the Sentience Smart. How many sensors can we integrate in the Sentience Smart?
Okay, so the Sentience Smart itself, so the housed version, that one just has one slit or one port for these type of disposable electrodes, like the IttelSense ones or the other ones that we sell. So all the ones that have the very typical pitch at the contact pads, which like most of the brands on the market have. And it can fit a single one. But if you work like, so you've seen Kordel has used a lot of the EmStat Pico. So the EmStat Pico is, so this is a small guy, and this is actually a dual channel potentiostat or a bipod. So you could have two working electrodes there. So you could detect two things, but we also offer a multiplexer for the EmStat Pico where, with a 16-channel multiplexer, so definitely 16 channels. And depending on how your setup is, you could use a mode that can multiplex it up to 256. But this is multiplexed. Multiplexing means it's a switch. So you would switch between the channels. So, if you use Kordel's method, which is very fast, that could work very nicely if you just switch through the sensors. But if you have, of course, the classic electrochemical things, which take like 10, 30 seconds, then you would, with, let's say, even with 16 channels, you would need 160 seconds at least to get through like all the sensors. That would take very long. That's for the switched one. But of course, again, the EmStat Pico is rather small. You could also implement multiple of them, maybe on the same robot, depending on what type of robot you have. If we think of drones, yes, you have limited by weight. But if we look already at our Roombas or at like other vacuuming robots, from the weight that they can carry, you could put like a whole analysis system on top of them, I think.
Great, thank you, Lutz. Another question, but this one is for Korderl again. How can robots handle uncertainty and ambiguity when multiple odors produce similar or overlapping sensor responses?
So that's actually a huge problem, or a huge opportunity rather. And that's why I've tried to build some of these tools for data collection, because it's not yet well understood how aromas map to chemical molecules in the world, right? If something smells fruity, well, what chemicals actually contribute to that? Which molecules actually contribute to that aroma? There are a couple open data sets like Good Sense dataset, Leffingwell dataset that try to explain this. However, there's a real human element, because something that smells fruity to us might not smell fruity to like a dog or a moth, right? So it's again part of that, from my perspective, the combinatorial patterns that we see in olfactory sensors. If three of them fire, maybe it smells fruity. But if two of those three fire, olfactory neurons fire, then maybe it smells something, it's more sulfury or something like that. I'm using this as an example, but there is a big opportunity to try to align how humans interpret scent with how robots interpret scent in AI, because robots don't smell fruity, they don't smell sulfury or musky, they smell nitrogen dioxide, sulfur, toluene, acetone. And that's what the sensors are trained for. So how do we, there's already an alignment between machine and man here. And so if we can build tools to try to translate those together, that will be hugely beneficial for, not even just AI and robotics, but neuroscience, biology. There's a lot of open opportunity there. So please help.
Sounds good. Then there's a question from Tim Gibson. He mentions I've been working on VOC detection since 1991, and in his experience, it's the sampling protocol that gives you the edge on VOC detection and potentially quantitation. And he's asking, have you tried pre-concentration sampling protocols to enhance the sensitivity and selectivity?
Yes. Yes, we've tried that a bit, probably not to the degree you have. A lot of what we've done for changing the sampling protocols is a toggle between open circuit potentiometry or differential pulse voltometry to understand, again, is the sensor drifting, and then understand Am I at baseline for a sensor, or am I sensing stimulus? So switching, I guess, processing techniques during the middle of like a navigation session. I guess that's not pre-processing. That's more active processing in the middle of the task. I could probably give pre-processing a little more emphasis. So if you have any good papers or any good strategies, that's something that I could probably consider a bit more.
Right, thank you. Then a very short question. Could it also possibly, or would it be possible to detect pathogens?
I'm not a medical expert, but if I recall my work from working in breath, pathogens are possible to detect. Maybe not pathogens themselves, but indications of pathogens. So, for example, like a lot of what we were working on with breath is we weren't looking for medical conditions themselves. So, like maybe COVID, right? If you're trying to detect COVID, you're not actually detecting the virus. You're detecting your body's response to the virus, which is several different chemicals. And that's actually pretty important because if you can understand those correlations, you can understand how to detect things without actually even detecting them at all. You're not detecting the thing. It's like if I walk into a room, you might not see me, but if you smell my cologne, it's a good indication I was there. So by analogy, with pathogens, there is a lot of research that suggests you can do something similar if you can understand the consequences of what those pathogens produce in your body.
Great, thank you. Then a question from Alina Vasilescu. Can you provide any details on how the electrochemical measurement is done? Is it like an electrolyte, and what happens with it as the drone moves?
So, yeah, with electrochemistry, the sensors we buy, as I mentioned, are all third party, and we coat them with an electrolyte or an ionic liquid, and we use a very small amount of ionic liquid that if you were to use it for an extended period of time, especially in like a robotics and industrial setting, it's going to it's exposed to debris. And so we're trying to make it so that we don't have to basically change the sensors out after every session. Every few minutes, I've got to change sensors because there's drift or there's a bunch of debris from the rotors pushing up debris onto the actual ionic liquid that's exposed. So we're trying to solve that more. That's more like an engineering and a longevity and a scaling problem that will have a lot of benefit if we can solve that. But yes, electrolytes are coated onto the sensors, and depending on what chemical we're looking at, we either use the same electrolyte and switch the reduction potential that we're looking for, or we change the electrolyte altogether to look at a different chemical compound.
All right, thank you.
There, like another follow-up question. Sorry, does then the ionic liquid make it selective because only certain compounds from the air will dissolve in the ionic liquid, or what is like giving the selectivity then to the electrode surface?
The selectivity is due to the ionic liquid and then the potential at which we set to sample. For example, like amperometry, we can set it to 600 millivolts or 800 millivolts, and that will look at a different compound or different family of compounds, if you will. Yeah, does that answer your question appropriately?
Okay, thank you. Yeah, there's still quite a few questions left. We're gonna continue for a few more minutes, but I would like everyone to tell them, like, please upvote questions that you already see that you like, and then we can answer the most important questions first. That'd be great. Let's see if there's a
Maybe that's also a good point to point out that there will be a recording. And that we will send out to all the registered people. So also your colleagues who have missed the webinar can rewatch it later. Or you can rewatch it if you just missed a part or if you just want to hear an argument again. Okay.
Great. Then there is another question. There are lots of questions still. It's about COVID, actually, this one. So there's a person, this is actually Wolf Dietrich Meyer called, and he's asking, like, I've lost certain smell due to COVID. And for example, you can't smell fried onions anymore. Could a sensor in a partner's nose and be a possibility, and to send that information to an actor's nose as well, and then to his nose? Would it be possible?
Yeah, so for anosmic research, this is pretty interesting because you can build a nose prosthetic, right? And if you do research on electronic noses, you'll see various things out there. But if we can build a prosthetic device that is analogous, truly analogous, on par, representative of the human nose with all the olfactory receptors, then yes, you could do just as you're suggesting, by sending the signal. But I don't think we have an analog to human nose yet, because we have so many receptors, thousands of receptors in our nose, and we haven't replicated that into a small enough form factor that can do real-time processing, several sniffs per second, if you will, to enable that to be practical in the real world. But in theory, what you're suggesting could definitely be done if we can improve the hardware a bit.
All right, thank you. Then there's a question from Han Fan, and he mentions very impressive work, and he wonders when you describe the work that projects the multimodal information into the text decoder, do you use vision as the grounding modality?
So we played with I played with a couple of different configurations, and the best thing I can come up with is using vision as the grounding modality. Now, as I learn more, that might change. I get different performance if I use vision or text as a grounding modality. But because so that I mentioned the Sigma app that I built to do data accumulation. We've got microphone data, we've got olfaction data, vision data, inertial data. You could technically build a model that grounds each of those modalities differently, each of those modalities individually, and then tries to understand or look at the performance to see if one is more beneficial over the other. So vision for the one that I published is the grounding modality, but it actually be worthwhile to try to do more analysis to understand what happens if we change the grounding modality to like audio or olfactory data. I would definitely apprehensive to make olfaction the grounding modality, just because there's so much that is not understood. Again, a lot of the data that we see out there is for basically aroma and chemical compounds is not 100%, I would say, representative. So that means there's a lack of training data, which means there's an opportunity to gather some to make olfaction the grounding modality in such models. But yeah, right now the one that's published is using vision as a grounding modality.
There's just one final question from Arak Roisman, and he's asking, are you familiar with the research from Professor Hossam Hayek from Technion, Haifa, Israel?
Yes, if I remember correctly, they're the ones that are doing the olfactory receptors from I think they're moths, and then so actually using biological olfactory receptors to and processing the data from those, which works quite well, and it's really interesting research. I think that's the same group. If I'm mistaken, I apologize, but that's what immediately comes to mind.
All right, great. Thank you. Lutz, I think it's time to wrap up this webinar.
Oh no, okay. Great. Okay, so thanks again, Kordel, for answering all these questions. We will check the possibility if we can take a few of the unanswered questions and have them answered and send that together with the recording out in a newsletter. So everybody who didn't get the answer to their question, this way also has a chance. Furthermore, of course, you all have the chance, if you wanted to reach out to Kordel, if you want to start a cooperation or just maybe discuss something in detail. So maybe, Kordel, can you tell us once more where people can find you or how they should contact you?
Yes, so you can find me on LinkedIn. I do also have an X account, or just email me is probably the best way. Anyone that is interested in contributing to building the sense of smell for machines and trying to enable olfaction for artificial intelligence and robotics, I would love to talk with you and try to collaborate to try to make this effort more proliferate. There's a lot of opportunity here. And I mean, it's synonymous to what computer vision and computer audio were back in like early 2000s. So we have a lot of opportunity to make an impact. Please reach out, kordel.france@utdallas.edu, or kordel.france@gmail.com, or the social media platforms I mentioned. But I'd love to speak with you, please.
Okay, great. So thank you. So thank you, Ardi, for supporting us. Thank you, Kordel, for providing us all of that. expertise. Thanks everybody for watching and taking part actively in the webinar. As mentioned, there will be a recording and we will send it out to everybody who has registered. And I think that's it for today. Hopefully you will join us next time again. So everyone, have a great day. Bye-bye.
Thanks all.